Hello, my name is Albert Mishra, and for my first problem, basically said that you're getting ready to cook and that you have that you're in a kitchen of a small house. And so while you cook, you want your house to be a certain temperature. And so I'd give you the ambient temperature outside, the surface area of the wall that's exposed, temperature inside, and that you have a fan running inside, so the coefficient there. And then I say that assume constant thermal properties, and so we just need to figure out the cooling power required to go from a certain degree to a certain degree. So for the first part, it's just Newton's law of cooling, and get an answer there. And then for the second part, I say that you turn on your stove, you put a pan on there, and I gave you all the dimensions for the pan, and then that it's a steel pan also, so you know the emissivity. And so then I say, okay, you forget that you left your pan on there, and then you took it off and you hung it up. And so after you hung it up, you walk by and you think that it's about 60 degrees. That's just a guess that you have. And then, so for this part, I want what we're trying to determine is the radiation from the pan to the surroundings, depending on the guess that you guessed, and then find out if the temperature that we guessed was close to the value through lumped analysis. So for the first part, we assume that it's a uniform pan temperature and that the surrounding is black body. And we assume that convection from the pan is basically negligible. And then for the second part, we ignore the sides of the pan and we just assume like it's just a plate basically, and that there's uniform temp throughout the pan. So for the first part of solution, use the Q radiation equation, and you have all these values. You have to figure out the surface area, plug all that in, and then you get a value for the radiation. And for the second part, we know the thickness, we know the time, so we figure out the B number, which gives us a value of inverse seconds, and then we just plug that into the equation for lumped analysis, and we are able to just solve for the temperature, which we see that it's 52 degrees, which is pretty close to a guess of 60 degrees. And for my second problem, I say that you have a brass cylinder and you basically stick it in your stove, and I give you certain temperatures, and I ask what the temperature of the center of the cylinder would be after 10 minutes. And my assumptions are that heat conduction is 2D, axially and radially, and that we have constant thermal properties. I needed to find the properties of brass at 25 degrees, and that was on table A3. And so in order to do this properly, the solution basically all you need to do is intersect the cylinder in the middle with the plane wall of thickness 2L, which equals 10 centimeters, because that's how tall it is, and at a radius of 9 centimeters, because that's the center part radially. So what you have to do is figure out BO number, Fourier's number, and then go to table 4-2, figure out the constants, plug it into the appropriate equation for a plane, and then you do the same thing for the cylinder. You do BO's number, Fourier's number, figure out what the value is based on BO's number from table 4-2, and then you just plug that into the cylinder. And then basically, since it's 2D, all you do is you have to multiply the theta plane and then the theta cylinder. And when you do that, then you can set that equal to the temperature differences, and then you can just solve for the temperature in the middle. And then for problem 3, I said that you have a vessel that is filled with carbon dioxide, and you have it a certain distance below the water. And so for the first part, I asked to figure out the mass loss of the CO2 from the vessel to the rubber, and then I asked to figure out the time it takes for the gas to travel 10 centimeters from the top of the vessel through the water. For the first part, the assumption is that the mass diffusion steady state, and then for the second part that it's transient, and that there's no CO2 in the water for the second part either, and that the water CO2 contact is constant. And for this, we needed some properties. So diffusivity constant of CO2 in rubber, table 14-3, diffusivity of CO2 in water, table 14-3, and CO2 solubility in rubber, that was table 14-7. So for the first part, all you have to do is determine the density, and then you could figure out what the mass diffusion was by just another form of Fick's law. And then once you just plug values in with the appropriate area, you get the mass diffusion there. And then for the second part, we say that it's analogous to figure out the second part, it's analogous to 1D transient heat conduction, but this is for mass transfer. So you use this equation here. And then since the initial concentrations are 0, you do that. And then we said that this value here, it has to equal 20% So then we just set that equal to the error function, and then we can figure out what the error function equals from table is 4-4. And then from that, we're able to determine the time and then the answer in days.